All right, so let's continue where we left. So now we say the following. Whether you have the graph that you can already use the adjacency matrix, so if you have some other data points, you try to make a affinity matrix out of it, conforming to these rules. Another thing what you might want to do, and I cannot switch the slide for some reason, let me try to reboot my something is funny. Sorry for this. Okay. Okay, so another thing I didn't discuss is how we describe affinities, and of course that will be problem dependent. Is given your two data points, what does it make? What sense does it make to extract certain similarity function? But very often people would go to some kind of cosine similarity dot product or whatnot. But you can, but you should use the similarity measure that makes sense for your data set. And of course, make sure that it produces a positive number, where 0 is the no similarity at all, and the large number would indicate very large similarity. Now, the problem you might have is that if you deal like this with your data set, you might end up with this affinity matrix that is dense. And for theoretical computations, it doesn't make any difference, it's fine. But in practice, if you'll have millions of data points that will produce million square dense matrix, you might not be able to extract graph spectra. And graph spectra, as you remember, is basically eigenvalues with associated eigenvectors. So what you might need to do later is basically to sparsify it, because in some sense the information that this affinity matrix carries will not hurt a lot if you say zero the values that are close to 0 anyway. So you will, to some extent, if you think of it as a graph, and the dense matrix, or where there are no zeros, is a fully connected graph, but now suddenly it has links that have weights depending on what's in the cell, and you might have a lot of links with a nearly 0 weight. So that is as if you had no edge there in the graph. So you just zero it. So the only thing what you have to make sure is how you do that. And sometimes you, for example, you could say I either take a threshold and then after the threshold I just zero, or you say that I keep k nearest neighbors for every node, so that you say preserve some degree for this newly constructed graph. So say if you have a specific row I, it looks at all the affinities to all the other nodes, and you say take the k largest. Okay, that would be the. But you have to make sure that if you do it that way, you might end up again with not symmetric matrix, so you have to make it symmetric in the end. Okay. So again, you just have to somehow move from if your computational power does not allow, from the dense matrix to sparse matrix. And in many real-world scenarios, because there will be islands, and therefore there will be a lot of empty spaces, unused sort of links, you can zero it without the loss of information, you can do it. Or if you're lucky, you start with the graph already, and with the adjacency matrix, you can go on from here as if you have your affinity matrix as adjacency matrix. So now, spectral partitioning. Having this, what can we do? How can we now cluster it? And I will not tell you why, I'll just state the sort of magic how the spectral clustering gives us clusters. If you want to understand how, I posted the videos from this advanced data mining course. But for now, just think that this magic happens. Somehow you have a matrix that we can extract eigenvalues and eigenvectors, and it will give us somehow a good clusters. So now the other thing is that once we extracted A, it might not be the end of the story. A is this affinity matrix or adjacency matrix, right? We might need to do something more with that. But if we have only A, spectra of A helps us already to optimize for average degree or weight. Remember, average degree is our internal measure where you look at all the how many red links there are in your cluster normalized by the number of nodes. That's the average degree. Or if you have not 0 ones but some numbers, it's actually average weight. So if I have, say, 5 links with the 5, 7, 3, 2.5, whatever the weights, I would use an average weight. Okay. So if you want to optimize, if you want to extract clusters that optimize, that make the best, sort of clusterization, that have the highest average degree or average weight in the clusters, we have to look at the spectra of graph A, and that means we have to look at the eigenvectors associated with the largest eigenvalues. In the next slide I'll have to show you what exactly to do, but that would require having A to use some kind of tool to extract largest eigenvalues and associated eigenvectors. Okay, so if you want to optimize for that measure and extract communities that way. And as I said, that depends on the domain. And maybe if you are an attacker and want to do edge cut, that's not the way to go. If you're an attacker, you might want to, for example, go for ratio cut, where in a sense you look at the blue edges. And if you want to optimize the clusters and extract clusters of ratio cut, you need to a little bit change this A and make out of it Laplacian. Remember, you have to first make a degree matrix out of A. So you just will sum up all the weights and make in the diagonal all the weights from this affinity or adjacency matrix A, and D minus A will give you Laplacian. And now spectra of Laplacian magically, again I don't say why, but believe me, helps to extract communities that are best for ratio cut. And then we need to look at eigenvectors, but not with the largest eigenvalues, because suddenly the Laplacian has a bit of different behavior. Laplacian would, again, this is just have to take it for, for a face value. I don't explain why, but in this case you need to look at the smallest eigenvalues. So I can give you a small sort of glimpse why the largest eigenvalues somehow represent the first sort of eigenvalues represent the first best partitioning of the cluster, and the eigenvalues gives the size of the internal edges here. While here the smallest eigenvalues give given the best clustering you can extract the size of the outgoing edges. And of course, for the ratio cut you want to minimize, so you want to take the smallest eigenvalues, while here you want to maximize, you want to take the largest eigenvalues. So that's the sort of the computation behind, but if you want to be more thorough, you have to, you look at the other lectures to see why. And this is actually probably the most, or one of the widest used spectral clustering technique. Is basically many people do it on ratio cut, and if you want just to cut into two, I mean we'll later talk about how to cut into K cluster, but if you want to cut into two, you actually take a second eigenvector. That means you look at all the eigenvalues of Laplacian, you sort them to the ascending order. The first one, by the nature of the matrix, will always be 0, and the second one will be something a bit more than 0, and the second eigenvector associated with that eigenvalue will be called Fiedler vector. And from this Fiedler vector you can very easily do the bisection of the graph, and we'll see how in the next slide. So now again, if you want internal average degree, you go for spectra A and largest eigenvalues and associated eigenvectors. If you want ratio cut, you go to Laplacian and go for the smallest eigenvalues and the small associated eigenvectors. And then we'll see how to proceed further. And now if you want to have internal and external, you can go for the conductance measure, and then you would need to look at the a bit more ugly matrix, which is a degree matrix to the power of minus half times a times d to the power of minus half, which we call normalized Laplacian. And in that case, we conductance we try to maximize, and then we look at the eigenvectors associated with the largest eigenvalues. Sometimes, again, because there are different namings, sometimes normalized Laplacian is known as the identity minus this, and then you need to take the smallest eigenvalues. But just to make sure that if in some papers you see normalized Laplacian like this, then you cannot use this bullet. You have to go for the smallest. But for now, if you see this, then you go for the largest eigenvalues. Okay, and later I will also show how you can do the same with for the modularity. You need to work with the modularity matrix B and extract spectra from there. But for now, what I want you to remember is that if you chose one of the goodness measures from one of these categories, and if you prepared sort of your affinity matrix, which you can almost look at as a graph, and sometimes you have a graph by definition, sometimes you sort of construct a graph, you sparsify it, then you can extract these eigenvectors and eigenvalues, and we'll show in the next slides how very easily you can do the graph partitioning there. And I will not talk about the complexity of extracting the eigenvectors and eigenvalues, but you have to, I mean, there are many tools, and they are very effective if you have a sparse matrix and if you request not all the eigenvalues and eigenvectors, but only top k, like top smallest or top largest. So then they can be relatively doable, because of course if you want to extract n eigenvectors and for very large graph or matrix, that would be first useless, because you don't need usually you need only very few of the eigenvectors. If you have n, 100,000, you might need only 10 dominant eigenvectors, not 100,000. So you can be quite efficient if you know what you're doing. But of course, if you go brute force non-specified matrix and extract everything, you might get stuck, and then your algorithm never completes. Okay, so now let's look at this Fiedler vector. So this is an example of a graph, and this is the values of the second eigenvector. And what you see here is the following. Here is this eigenvector values ordered by their values. And you can see that the Fiedler vector would have negative values associated with the one part of the cluster and positive values with other part of the cluster. Because it sort of tries to bisect in such a way that it assigns the IDs that are negative to one side, positive to the other side, and by some summation, which basically counts the cost on these links, it tries to minimize this cost. And if you assign in such a way that, for example, every node here corresponds to this lower cluster and this to the upper cluster, it would, by just looking at so if you do the following, if you extract, as I said, you have your data points, you make a affinity matrix A, then you make a Laplacian L. From Laplacian, you extract the eigenvalues from 0 to somewhere up, and you take the second eigenvector associated with the second eigenvalue. The first eigenvector is not interesting because it's 0. If you take the second one, just by looking which one is negative, which is positive, can tell you which goes to the one cluster, which goes to the other cluster. That's magic for you. Okay, yes?
What happens if there's more than 2 clusters?
Now we come to that. What's if it is more than 2 clusters? So let me just finish with the 2 clusters, and then we'll complicate things further. So the default thing, like a hello world for spectral clustering, is the following. you say you just want to bisect only two clusters, no complication. You build out of the graph this affinity matrix and then Laplacian matrix. You decompose it into the eigenvalues and associated eigenvectors. You take the second eigenvector, which is called the Fiedler vector, and then simply look which ones are positive, which are negative. And you put positive nodes to the one cluster, negative to other cluster. And of course, there are a bit more complicated ways to do it, but I don't want to bother you there. It's just for Fiedler vector, it's a good enough negative, positive, and you are bisect. Now, yeah, so basically this is the splitting point. And I mean, there are other ways to complicate things. You might not do it on zero, basically positive, negative, but you might want to go through, sort of a swipe through all possible points and then evaluate the goodness at, maybe, if you cut here, if you cut on 0.1 or maybe 0.5, but that's split on 0 or a median would be good enough for your initial hello world grouping. Yeah, and then you basically get in two clusters. Now, of course, as your friend just said, what happens if you want to split k-way or k partitions? Maybe you can suggest me already? Yes.
We can continue splitting the new clusters recursively and having a good stopping criteria.
Excellent. So that's exactly what was proposed. It was called recursive bipartitioning in 92. So if you were in 92, you could have published this paper. And basically, that's exactly, you partition and then you take a cluster as a new graph, the subgraph of the new graph, and then you do the same thing and keep on cutting. But of course, now you can see this. It doesn't maybe very naturally cuts the graph. First of all, if you have, then you should have like a 2 to the power of something clusters. Maybe you want to have some, I don't know, 13 or 7, or it will be harder than which to cut, which not. It's not preferred usage of this way. What is preferred is actually to cluster multiple eigenvectors. And now, how do we do it with that? So what we do is actually the following. And maybe I just want to remind you one thing. Eigen decomposition. Where is the eraser? Here. Eigen decomposition is the following. So if you have this matrix, say our matrix A or L, let's say A, doesn't matter. You can decompose into 3 matrices, which we call X, let's call sigma, and X transpose. X transpose. And it would be decomposed perfectly if the columns here eigenvectors and rows here eigenvectors. Here is a diagonal matrix and here are eigenvalues from biggest to smallest. Okay? So that's eigen decomposition for you. Now, what does that mean? For example, biggest to smallest. So here, if you talk about A, this is some big, and then go smaller, smaller, smaller. What it does in effect, this, for example, given a cell, this cell is equal to, in a sense, the multiplication of this eigenvector times this plus the second one plus this times this, and basically the weight, you multiply always the eigenvectors, you sum them up and weight it by this, by the eigenvalues. And at some point eigenvalues become very small, so the weight is almost negligible. So the sum, if you want to reconstruct, say there was a value, I don't know, 7, if you want to reconstruct 7, you might not need to go to the sum all the way down. Maybe it's enough to stop where the most significant the weights are, and the rest that next to 0, you just ignore it. And by ignoring, meaning that you ignore this part and you ignore this part. Okay? And then you, in a sense, what you take the dominant eigenvectors, maybe only 10, times now the small 10 times 10 matrix, which contains the most significant eigenvalues, and these 10 rows. And this you ignore. And the value will be nearly the same as you started with. So that's the this is actually the dimensionality reduction technique. And there is a more known by also SVD. You can do it for any matrix. This is for if you do it for what's the name? The square matrix. Thank you. But you can also do it for n times m matrix, and then you can do the same thing. It would be n times some kind of r times r times r times m, and you can reduce the dimensionality that way if you choose wisely this sort of this singular values. It's called singular values, and in this case it's actually the eigenvalues. In this case it's a bit different than eigenvalues, but it's very similar to that. So yeah, so what you do is the following. What you do in effect is you have a high dimensional space, because now your graph lives in a high dimensional space with say zeros and ones. So every node is described by a vector of, I don't know, say 1,000,000 if you have 1,000,000 nodes. And now what you say, I'm going to collapse it to a very low dimensional space, maybe only tens or maybe 100 instead of millions. So you actually cut a lot of things, while I will not lose much of the information. And in this case, for a specific if you talk about A or L or normalized L, it acts in a sense that it's what you get, say the dominant vectors give you now for every node from 1 to n a new coordinate that is in a low dimensional space. For example, this node I will have a coordinate instead of being say 100,000 and 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, now has a coordinate that is something that will be dense, because eigenvectors are usually dense, with some kind of coordinate in a low dimensional space, maybe in 10-dimensional space. Okay? And in this 10-dimensional space, what it does, these different techniques, let's say the average weight or conductance, it puts together into such clusters nodes that correspond to the clusters in the graph that are cut best by this specific value measure, say conductance or ratio cut or average degree. So what you have, if you have this multidimensional, very sparse, unclear matrix, not clear how to partition, you do eigen decomposition, you take the dominant eigenvectors and dominant bases in now in a low dimensional space, maybe 3, and there the nodes would have quite separated, if they were naturally quite separated clusters, they would have coordinates where they are very well dispersed, because by the magic of mathematics there, they try to push them together as much as possible. And then a simple k-means could find the clusters easily. So in effect, what we do is the following. We take the k-dominant eigenvectors, as I said here. We now assign, every node gets a coordinate in this newly acquired low dimensional space, and then in this space, simple clustering like k-means will discover the clusters, because the spectra forces it to separate into the clusters that that correspond to our sort of this, where was that, to our requirements, like average degree would be for A, ratio cut for Laplacian, conductance for normalized Laplacian, and so on. So how would it work more in practice with the several vectors? So here was the simple example. Now let's say a bit more complete example, like 4 clusters. Now we see by our naked eye it's a 4 clusters. So if you look at only this Fiedler vector, you could see that still by just looking at the negative and positive, you could only do a bisection. Probably it would be here. It would be the negative guys here, positive here. And if you now want to discover further clusters, you might want to look at the, not at the, only at the second vector, but now also the third vector. And the third vector would look like this, right? Because now what it means in effect is that if you bisect with the second vector, you need to take these nodes and these nodes like into the 2 clusters. And if you bisect by the third vector, you would need to take this and this, so maybe that guy and that guy in one cluster, and that guy in another cluster. And that might not be as good cluster as this one, because this had only 1 cut. Now the other one would have 1 to 3 cuts. And that, in a sense, corresponds to the eigenvalue, because the eigenvalue x2 was probably very low, corresponding to 1 cut. An eigenvalue of this one will be a bit bigger, corresponding to these several cuts. And you can look at the further on, but if the more you cut, if you run out of the natural clusters, then the spectra will need to cut inefficiently, and then the eigenvalues will be very high, because it will correspond to a very unnatural heavy cut. So what you do, for example, if you want to cluster that way, you could say the following. Now I use, if I want, for example, the components only for x2 and x3. And then these guys would be positive in x2 component and positive in the x3 component. These guys will be positive in x2 but negative in x3. This one will be positive in x3 but negative in x2. And this will be both negative in both components. And k-means would have no problems of separating them. And of course you can ask me now how to know decay. And decay, it's again what we discussed before. It corresponds to the eigengap, meaning this set of eigenvalues. We have to see how they behave, because we usually order them from biggest to smallest, or for the Laplacian from the smallest to biggest. How it behaves if it is sort of from 0 goes up. That means there was a good partitioning, quite good, and then suddenly at this point it's not good partitioning, because the eigenvalue, the size of eigenvalue, indicates how good or bad we can cut specific cluster. So what usually people do is the following. They say you look at the difference between every subsequent eigenvalue and see where is the biggest eigengap. So if you have, for example, eigenvalues for, probably this is for matrix A, because it goes from the biggest to smallest, you can see that the biggest is from lambda 1 to lambda 2, so you choose 2 clusters. And I can show you some real world, but not real world, but a synthetic example, but on MATLAB. Can you see now? Let me. So why it's crashed? Okay, let me kill it. Okay, so here I made a simple graph of, I think, 4 clusters. Yeah, so you see there are 4 clusters, and I forced it that every cluster should have mostly, I don't know, maybe 80% links to its own cluster friends and 20% to other clusters, so it's clearly clustered. And now what I did, I did the composition of this graph into spectra of L, A, and it's actually a random walk matrix, but we didn't talk about. Okay, let's talk about only L and A, the adjacency matrix and the Laplacian. Now, here you could see I ordered from biggest to smallest, so from smallest to biggest eigenvalues. And of course not all of them, because there are, I don't know, maybe some thousands of nodes. Here I took only the top 10 smallest. So you could see that there are small, up, then big, and then continues very big. And for A, it's other way around. It goes from the big goes to the small, and then being small altogether. So now how does it look? Let's say, how does eigenvectors look like? So here I could, okay, so let's say I show you. So now you see eigenvalue is the following. The first eigenvalue is 0. So it's not interesting, and the eigenvector would be something around 0. I mean, not, it's constant, so it's not interesting eigenvector. The second eigenvector is already something more interesting, because you can see already that if you go see 0, then you'll have a clear, these guys and these guys will be negative, this will be positive. If I go to the second or the third eigenvector, it now gives another partitioning. So this will be negative, negative, positive, negative. And you can go on like this, and you can see that as long as there are these natural clusters and the associated eigenvalues are low, meaning that there is very little cut for this type of partitioning, we have quite good clusters. But then later you see that what happens here, it was eigenvalue 0, 0.3, 0.3, 0.4, and suddenly 22. That means spectral clustering here had a hard time to find another way to cluster things, and the way it found had a very big cost. Because when I constructed the graph, I only made 4 natural clusters, not 5. Therefore, when I forced, in a sense, with the 5th eigenvector to find a 5th cluster, the spectral clustering found it, but the cost was very high, and it's reflected in this eigenvalue, which now also we can see there is an eigengap. So if we now look at how this looks, then it looks some kind of very strange suggestion. You know, one is some nodes had a super low values. Anyway, so basically what I want you to remember is that what you usually have to do, you plot top k dominant eigenvalues and see where the gap appears. And then you take only those eigenvalues and associated eigenvectors for, say, partitioning before the gap. That's the trick. And then again, if you do it for L, you solve for conductance. If you do it for A, you solve it for average degree. If you do it for normalized Laplacian, no, for L you do it for ratio cut. For normalized Laplacian, it's conductance. So this, if you know these tricks, you can basically already start clustering. And I think some of you even took the paper that proposes the spectral clustering, and that's basically the meaning behind. So coming back, so the last thing is just that, I mean, it's a similar trick with if you want to optimize for modularity, sort of for this global goodness, you have to construct modularity matrix as we discussed before. Is the difference between the adjacency matrix to observe in reality minus the probability that the edge appears at random. And then you calculate the eigenvector of the largest, most positive eigenvalue, and then you do the basically bisection with the positive and negative, same like with Laplacian. And I think I showed you before. This is the also hello world graph for graph mining. Is this the karate club graph where there were two instructors that had some fight with each other, so they were not friends, but they had some students, the karate students, and then eventually they split the club into two, and say by one of the initial papers were using modularity spectral clustering to bisect the graph and show that you can predict the schism in the karate club. Okay, so just to recap of what we said today, there are many community evaluation measures, and there are no goods or bads. It depends on your domain, and you can either use existing ones, you can use this one size fit all, take the triangle ratio or the conductance, or you can try to look at your specific problem and see what would make most sense, and then later you might want, once you define the evaluation measure, you want to define an algorithm which would solve for it. Because again, if you would define that the best is your average degree, but you solve with the Laplacian, it will solve on a ratio cut. And it might not be, it might be good enough maybe for your all practical reasons, but that's not mathematically sound because you solve for other issues. And maybe if you invent your own evaluation measure, you might even need to invent your own algorithm on how to extract the specific cluster. But if you use one of the existent sort of evaluation measures from the 4 established categories, and you want to use spectral clustering, which basically, if you have a sparse matrix, then many tools could handle it without bigger problem. You can basically use, for example, a spectra of A to solve of the average degree, or a spectra of L for ratio cut, spectra of normalized L, normalized Laplacian on conductance, and modularity, spectra of modularity matrix B to solve on modularity. So that's the tricks that that basically you can use to use spectral graph clustering to cluster your graph. Do you have questions? Is it scary or is it easy? Somehow you were a bit more talkative in the previous lecture, so I'm a bit scared if I am not comprehensible. Because don't be afraid to ask. I will say that I don't know maybe, because for me it's also many things are not clear. I mean, some things I only, you learn for a specific type of setting, and then if you get a new setting, some kind of a strange directed graph, and then some spectra cannot maybe work or be very unclear and so on. So but this for the default, yes.
So we need only one eigenvector to identify clusters, but we need eigenvalues to identify which eigenvector we're going to use.
Not exactly. You can have one eigenvector if you want to only cut into 2.
No, I mean for cutting into K.
Then you need more. With one, you might not be that I mean, okay, I see what you mean. Maybe this was a bit deceiving, because here I have only one vector, but somehow I could already see I cut here, I cut there, right? That's a bit deceiving picture, because in reality that actually gives us only one cut. The other cuts might be very fuzzy.
No, I mean we can use only X4 in order to identify the 4 clusters.
No, we need to use all 4, not only X4. So if you want to cut, into bisect, take one vector. If you want to have more, then you actually take, where was that? Sorry. where was, well, here. So if you want k clusters, you take k vectors, and for every node you give the coordinate that corresponds to basically to each dimension from every eigenvector. So you need k vectors. If you take only the last vector, it would be very small signal to extract the clusters. So the point is, you take k, the dominant eigenvectors, depending on the problem you solve, either associated with the smallest or the biggest eigenvalues. You take k of them, and the number of k you can look at from this eigengap, because sometimes it's not clear where. So you look where the gap happens and say that will be my k before the gap. And then having this k, I prepare this basically matrix, this k eigenvectors, and then I say that every node that I have will have now a coordinate in this k-dimensional space. And in that way, they will be very well separated depending on which eigenvectors you chose, from Laplacian or from adjacency matrix. So if you chose from Laplacian, it will be very well separated for the ratio cut. Okay? And then the separation can be very easily found by, say, just k-means. You use k-means in this low-dimensional space. You say k equals k, and then run it, and they will, without sort of, if the graph is clear, because sometimes the graph is not clear, that's another problem. Then maybe it's not separatable easily. So then you might have issues that we face with k-means in general. I remember where you start, how you put the case. But if you have a quite simple graphs like we had so far, basically any k-mean setting could very easily find these k clusters, and then they say these are my communities that I'm going now to output for your application, whatever you want to do with it. So no, so not the last eigenvector, all of them. And if you want to only for bisection, you can take only one. But then if you want two, you have to take more and more of them. Because to some extent, again, as I said from this multiplication, the most information is carried by this dominant eigenvalue and associated dominant eigenvector. And if you take only somewhere below there, if I only take only one component, not the sum of them, the information, the final sort of initial, this number will be very much off from what you started with. Because what you want in effect is to have this coordinate space that could reconstruct the initial graph. Because otherwise, and you can reconstruct, because most of these guys are, very small, for example, so they are almost insignificant, so we can reconstruct the initial graph. Any other questions? I think we'll probably stop here because there is now I only left with the link prediction, and I have 2 minutes, so I'm not going to cover it. But if you have some questions on the spectral clustering, please shoot and don't be shy. It's a very good question what you ask. No? Okay. Oh, yes?
Some of these things seem familiar to some of the matrix clustering things that we have done previously, like earlier in this course.
Yes.
So when is something called spectral clustering and when is something not called spectral
Okay, that's a very good question. So very often, I mean, again, I don't want now to sort of generalize, but I would think it sort of right-hand rule with the following. When you take a graph transformed to some matrix and extract spectra, meaning extracting eigenvectors and associated eigenvalues. I mean, spectra is nothing else as trying to reconstruct from this A these three matrices, and these two are identical because they are eigenvectors, and this is the eigenvector, this is eigenvalues. And usually the dominant eigenvector with the dominant eigenvalue gives some kind of, not always but very often, some kind of centrality measure. how good every node is. And for example, if you remember the random walk matrix, with some tricks and it's like equivalent to PageRank. So that's a dominant. And that's why we usually don't look at the dominant eigenvector for clustering, because this is as if you took one big cluster. What we do for clustering, we have to look at the further vectors, like the Fiedler vector and the further on vectors that tell us, and again by the mathematics involved, that they try to push things, they try to separate, so to give labels in this vector space to the nodes, so that whatever we're solving, for example, the ratio cut would be as minimal as possible, or the internal connectivity would be as maximal as possible. So writing will be the following. For clustering, you look at not the first but the subsequent eigenvectors and look at this as the low dimensional coordinate. So sort of you represent, next lecture we'll look at the graph representation learning, so that's a very similar thing. In a sense, you represent every node in a graph. A graph is a very complex structure, into a low dimensional space with some coordinate, and the space where it lives is defined by the problem you are solving, for example, conductance. But the others, what we saw before, we usually looked at the dominant eigenvectors, the sort of the main ones, like eigenvector centrality, for example, and that doesn't cluster for you, but it gives you the goodness of every node given one big cluster. So you could interpret that way. I'm not sure you could interpret that way Laplacian, because it's basically it's zero, but also could interpret it as a one big cluster with a cut 0, because if you take all the nodes into one, you say that my graph is one cluster, of course there is a cut 0, because there is no outgoing edges. So you can look at it that way. And in that case, what you measure is not which cluster you belong to, but how good you are within that cluster somehow. So the dominant eigenvectors you could think as some goodness for every node, while the subsequent ones try to push you together in certain clusters given the problem we're solving. Any other questions? All right, so then let's close it. Then that means we'll have one more lecture with me, because I didn't finish everything. But next time on Friday we'll have a researcher from Rice. He will talk about NLP and data mining of a natural language. Then week after, I think we have a Wednesday off, because now it will be many days off. Like the May is the best month in Sweden. So, and then on Friday we have another lecture. It will be either me or invited lecturer from on my ex-postdoc on privacy preserving data mining. And then I think I'll conclude week after with the link prediction, which is actually quite easy, so you will not be too as scared as with graph spectra. Okay, thanks guys. Have a good day.